Alright, so as we mentioned at the end of the video, the previous video, obtaining a Taylor or Maclaurin series is a very tedious process. And well, so what if, for example, what if we want to find a power series for this function or for that function or even this function, because well, we will, you know? So, I mean, look at how complicated the process it's going to look like if we were to do it. I mean, like taking many derivatives, having a product, having another product, the derivative of this ln along with its chain rule would involve rational functions, and well, it's just going to become a very, very horrendous hell to go through. So, I mean, it is possible in this case just use the results. So yes, in this section, and yes, I think mostly this section and part of the previous section, we came up with some power series representations of functions. So for example, in this case, in this section, we started talking about the series for the geometrics, in order to obtain power series representations for rational functions. And then we also deduct one for ln of 1 plus u. Alright, well, in this case we use 1 plus x, but of course if we have a function that is more composite, well, then we have to use this u. In section 11.1, in Taylor and Maclaurin polynomials, we also came up with a one for sine and cosine. But for those two series, we never talked about the interval of convergence until now. And in fact, no, we're not going to do the ratio test on this series to determine it, because they're given here. So we have this, we have this power series, this summary of series, and in parentheses you have the intervals of convergence. Check this out, the one for arctan, which arctan got derived from this one, from the one for the geometric series, So, but what recall that what changed in this case was the interval of convergence. In this case it's exclusive, but in this case it's inclusive for the endpoints. All right, and then one that we didn't know how it looked like was the one for the exponential. All right, and in this case, well, the interval of convergence is all real numbers. It's all real numbers for the intervals of convergence for the e to the u, sine and cosine. The other ones have other restrictions. And well, we are just going to use these formulas to come up with new series for other functions. So for instance, find a Taylor series for the function centered at the indicated number. Well, in this case, so we have the function f of x equals to f of x equals to e to the 6x. Well, if we write this as e to the u, then we need to state that u equals to 6x. So this will be e to the u, which has a sigma representation. Let's just use the formula from the definition box above. Let's use this one right here. All right, and that sigma u to the n over n factorial, where in this case u to the n is that's a 6x to the n over n factorial, which reduces to sigma n equals 0 to infinity of 6 to the n x to the n over n factorial. So that's the series representation. And in the homework, on the homework on MyMathLab, you might be asked to expand a few terms of the series. So all you have to do is, well, let's expand 4 different values of n. That's 6 to the 0, x to the 0 over 0 factorial plus 6 to the first, x to the first over 1 factorial plus 6x to the second, x to the second over 2 factorial plus 6 cubed plus, times x cubed, 3 factorial. Well, of course, this one goes on forever. Well, this one is going to be a 1, and then that's going to be plus 6x, the second term, and then that's a 6x squared. I'm going to need a calculator here. So that's 6x squared, and well, 6x squared over 2 factorial, so that's 6x. No, not this calculator. So this reduces to, so that's 36 over 2, that's plus 18x squared plus 6 cubed. Okay, that's the one I need to do. 6 times 6 times 6 over 3 factorial, which is 6. That's 36 x cubed plus. So you may need to even add more terms, but in this case 4 terms is fine. Alright, let's have a look at another example. F of x equals e to the 4x at x equals to 2. So number 1, okay, notice in this case it's the same function. Actually, it's the same function than the one that we did using the long process here, e to the 4x centered at a equals to 2. But instead of doing all this process that we did, we will do just the formulas. And by the way, the interval of convergence right here, so interval it's all real numbers, negative infinity to positive infinity, and that's because it's an exponential function. Alright, so f of x equals e to the 4x at x equals 2. So number 1, let's rewrite the function f of x equals e to the 4 times, well, number 1, the fact that the series is centered at x equals to 2, it means that an x minus 2 factor will, to the n power, will show up. Alright, so what do we need to do? So we need to make sure that, well, in this case, e to the 4 times e to the 4x, and in this case, well, I'm going to add a special version of 0. In this case, I'm going to subtract 2 and add 2, because if I subtract 2 and then add 2, that's basically adding 0, which still remains with the 4x right here. And then, well, I'm going to group this. I'm going to group these two. I'm going to group this right here, and I'm going to group this one right here. And I'm going to treat this as one factor, and then this is another factor. Alright, so this will be e to the 4 x minus 2 times e to the 4 times 2, which is the e to the 8. Alright, so let's see. And notice the similarity. I think from here you can tell where we're going. So this will be the e to the 8 that we got from the previous series. So let's see. So this will be, okay, so this e to the 8 will be at the beginning. I'm going to rewrite this, and well, this is the same as saying e to the u times e to the 8. Alright, where the u rather u equals to 4 times x minus 2. Alright, so now let's e to the 8th times the series for the exponential, which in this case is u to the n over n factorial, and our u is it's our 4 times x minus 2 to the n over n factorial. Well, I'm going to introduce this e to the 8th here. E to the 8th, 4 to the n, x minus 2 to the n over n factorial. And as you can tell, it's exactly the same as the previous example that we did by brute force, by doing all this. Isn't it the same? It matches actually. All right. And well, of course, the interval of convergence, so let me just call it I for short. Interval of convergence, so IOC, interval of convergence for short. I don't think this is like the official abbreviation, but I'm just going to do to make this shorter. So that's also negative infinity to positive infinity. And well, I'm not going to expand terms for this one, just use the example that we did before. Alright, so let's see. Let's do another one. F of x equals x cubed e to the 6x to the 4th power. Do you really want to take derivatives for this? Do a lot of product rules and a lot of evaluation things, but no things. The good thing, this is centered at 0, which is fine. So that's going to be f of x equals number 1 x cubed e to the 6x to the 4th. And well, so what I'm going to do is turn this exponential part into a u, where in this case the u is 6x to the 4th. All right. And well, that's x cubed sigma n equals 0 to infinity u to the n over n factorial, where the u will be replaced back with 6x to the 4th power. So x cubed 0 to infinity, so that's 6x to the 4th to the n over n factorial. And well, I'm going to simplify this first. X cubed sigma n equals 0 to infinity 6 to the n x to the 4n over n factorial, and then I'm going to introduce this x cubed into the summation expression. Because we have the same base x, what we do is add the exponents. Six to the n x to the 4n plus 3 in this case over n factorial, and that's going to be the power series. And again, the IOC, the interval of convergence, it's also all real numbers. All right, so now as again, because in this case on your homework you may be asked to expand a few terms, so expanding this a few terms, so that's 6 to the 0 x to the 4 times 0 plus 3 over 0 factorial plus 6 to the 1st x to the 4 times 1 plus 3 over 1 factorial plus 6 squared x to the 4 times 2 plus 3 over 2 factorial plus etc. Okay, let's just expand 3 terms. That's fine, that's enough. Okay, so that's 6 to the 0 is 1, 0 factorial is 1, x to the 4 times 0 plus 3, it's going to be x cubed, and plus 6 times, or rather x to the 4 times 1 plus 3, 7, plus 6 squared, which is 36 over 2, that's 18, x to the 4 times 2, which is 8, plus 3 11th power. Okay, let me do one more. Why not? 6 cubed, 4, no, that's x. 4 times 3 plus 3 over 3 factorial. So 6 cubed, which is 216. 216 divided by 6 is the 36. X to the 4 times 3, which is 12 plus 3, 15 power plus dot dot dot. Alright. Let's do a couple more examples. Alright, so for letter D, f of x equals x squared cosine of 9x. And number one, in this case, we're going to use the power series for cosine of x. Alright, so, okay, let's write this f of x equals x squared cosine of 9x. X squared cosine, let's call it u. And then, for in this case, u equals 9x. And then I'm going to write x squared and then the power series for cosine. And well, let's recall what the cosine, what the expression for cosine is, which in this case is this one right here, u to the 2n over 2n factorial with an alternating factor, of course. All right. N equals 0 to infinity, negative 1 to the n, u to the 2n over 2n, the whole thing in parentheses factorial. All right. And let's just go back and substitute for this. That's x squared sigma n equals 0 to infinity, and that's a negative 1 to the n, u, which is 9x to the n power, over that's a 2n factorial. All right, and well, so this will be x squared. Okay, let me continue over here. Let me get some space. So that's going to be x squared sigma n equals 0 to infinity, negative 1 to the n, 9 to the n, x to the, oh actually this one is supposed to be 2n, not n, 2n over 2n factorial, the whole thing in parentheses for the factorial part. Alright, so I'm going to introduce this x squared inside over here, n equals 0 to infinity, negative 1 to the n, 9 to the n, x to the 2n plus 2 over 2n factorial. Alright, so that's the power series for the function x squared times cosine 9x, which otherwise, I mean, would have taken forever doing it a long way, right? And well, because the interval of convergence for the cosine function, again, it's all real numbers, negative infinity to positive infinity. Even for any shifted function, well, this IOC, or interval of convergence for short, that's a negative infinity to positive infinity. And of course, well, in this case, I think I'm not going to do the terms expansion. So ultimately, the most important is how to get the sigma notation for this. Obtaining a few terms, I will just leave it as an exercise to you. All right, so let's see. Let's do one more. F of x equals x minus 3 to the 4th power ln of 1 plus x minus 3 centered at x equals to 3. Well, the function looks a bit complicated, but it's not as bad as it looks because, well, this x centered at x equals to 3 implies that we should have an x minus 3 to some n power, and in fact, if you observe, that's what we have in here. All right, so okay, so let's start by rewriting the function first. Okay, so f of x equals x minus 3 to the fourth ln of 1 plus x minus 3 squared. Alright, and in this case I'm going to write this in terms of u. But in this case I'm just going to write, okay, so x minus 3 to the fourth ln of 1 plus u, where our u in this case is u equals to x minus 3 squared. Okay, and well, we know a power series for ln of 1 plus u, and we're going to refer from the previous page. It's right here, sigma n equals 1 to infinity of negative 1 to the n minus 1 u to the n over n. Okay, so let's just go ahead and do that. So number 1, so that's x minus 3 to the fourth, and instead of ln of u I'm going to write sigma n equals, in this case, 1 to infinity of negative 1 to the n plus 1, or rather n minus 1 u to the n over n, and I'm going to replace u with this x minus 3 quantity squared. And well, this is going to be power of another power, multiply the powers, so that's x minus 3 to the fourth sigma n equals 1 to infinity negative 1 to the n minus 1, that's x minus 3 to the 2n over n, and I'm going to put this inside because this is x minus 3 to the 4, x minus 3 to the 2n. This is sigma n equals 0 to infinity negative 1 to the n x minus 3 to the 2n plus 4 over n, and that's the power series. And now for the interval of convergence, the IOC for short, interval of convergence, well, let's be careful here because for the natural log it's not all real numbers as the sine, cosine, and the exponential. This one has a different inequality here, so it's going to go from negative 1 less than u less than or equal 1, and in this case our u, I know the u had a squared over here, but in this case for the u I'm just going to take the x minus 3, okay, to make this simpler. So negative 1 u less than or equal 1, because otherwise we would have to do, you know, the long process, ratio test the endpoints, and then find out that the final answer is this. Okay, so negative 1 less than, that's an x minus 3 less than 1, and add 3 to the 3 sides of the inequality, that's 3 minus 1, that's a 2, x and 4, or in interval notation 2 comma 2 to 4, exclusive for the lower endpoint, inclusive for the other endpoint. And of course there's the other part of expanding a few terms. Well, that's something that I will leave it as an exercise. Let's do one more. So this one is actually a very typical home exam question. Well, so we have this rational function for which is 5 over 2x minus 3 and centered at x equals negative 3. Okay, what are the implications here? Number one, this means that we should see an x plus 3 to the n in our series. In other words, when we set up our u part, it has to look like an x minus 3. And well, number one, This looks like sort of the 1 over 1 minus r, or 1 minus u. Alright, so let's find a way to rewrite this in that form, and that also has an x plus 3 in the u somehow. Okay, so let's see, let's have a look. F of x equals number one, I'm going to rewrite the order of the terms in the denominator, negative 3 plus 2x. Alright, and then from here, this is where I'm going to do the trick of writing the special version of 0. So minus 3 plus 2 times x, well, negative 3 plus 2 times x. I need a plus 3 here. I can add that plus 3 provided I subtract a 3. Alright, so from here I'm going to group this. I'm going to group this one right here, and I'm going to group this one right there. Alright, and then I'm going to distribute 2 times x plus 3 and 2 times negative 3. Alright, so in this case, so that's a negative 3 plus 2 x plus 3, 2 times negative 3, which is negative 6, okay, all under 5, and then I'm going to have negative 3 minus 6, that's negative 9, plus 2x plus 3. So now here is where it almost looks like 1 over 1 minus u. We need number one we need to do two things here. Number one, what I'm going to do here is to, okay, so I'm going to divide both sides, numerator rather, not both sides, numerator and denominator by 9, because this negative 9 should be a 1, and in order to accomplish that, what I'm going to do then is to divide by negative 9 numerator and denominator. When I also divide by a negative, this positive turns into the negative by 1 from the 1 minus u. Alright, so let's go ahead and do that. So that's going to be 5 over negative 9. That's going to be negative 5 over 9. And that's negative 9 over 9. That's going to be the 1 minus 2x plus 3, parentheses x plus 3 over 9. And well, I'm going to factor out this negative 5 over 9 and write this as 1 minus 2/9 x plus 3. And doesn't that look now like 1 over 1 minus u? Oh yes, I know, it's a very interesting mathematical sorcery problem going on here. Alright, so let's see. So this will be, let's write this in terms of u. How about that? You know what, let me just go, no, never mind. And so this is our u, 2/9 x plus 3, and this will be negative 5 over 9 sigma u to the n, and goes from 0 to infinity, and back substitute for u. That's going to give us negative 5 over 9, sigma n equals 0 to infinity, and that's u, which is 2 over 9, x plus 3 to the n, which will reduce, okay, here, so this is pretty much our final answer, but we need to simplify this a bit further. Negative 5 over 9, n equals 0 to infinity, 2 to the n, x plus 3 to the n, over 9 to the n. But over here, I'm going to introduce this 5 over here. I'm going to leave the negative outside. Five times 2 to the n, x plus 3 to the n, over 9 to the n plus 1, and that's because 9 to the n times 9, the one outside, will be this. And then for the interval of convergence, notice the u in this case. Okay, in this case, be careful with the u, because our u will contain also those coefficients. So interval of convergence, that's u going greater than negative 1 and less than 1. And in this case, so that's a 2 over 9, x plus 3, less than 1, greater than negative 1. So let's multiply both sides by 9 halves. That's going to be negative 9 halves, less than x plus 3, less than 9 halves. And then add 3 to the 3 sides of the inequality. So that's a 3 times 2 is 6 minus 9. That's a negative 3 halves. X, and 3 times 2 is 6 plus 9, 15 halves, which in interval notation is negative 3 halves, comma 15 halves. Of course, we can just use this in a way shortcut. It's not a shortcut, it's actually using the result. Otherwise, if you're not sure how we got this, well, you can go through the long process, do the ratio test on this one, and then test the endpoints. You should get this. And one more example. I believe this is the last for coming up with series. Well, we have f of x equals 7 to the x. Well, this is an exponential function, all right? But it's not an exponential function of a base e. All right, however, on top of that, it should be centered at a value other than just 0. So it's going to be a Taylor series, not a Maclaurin series. That means an x plus pi to the n should be there. Okay, so let's see. So let's start rewriting by rewriting the function again. F of x, okay, equals 7 to the x. All right. But in this case, I need that x to be shifted by x plus 7. 7 to the x plus 7 minus 7, all right. That's a, no, not 7, actually it's pi. Pi minus pi. And I'm going to group this the following way. So I'm going to have this 7 to the negative pi times 7 to the x plus pi. And this is the one that we're going to use to obtain the series. But again, this is not an exponential function of base e. However, we're going to use the properties of exponential functions and logarithmic functions. You know, so there's a couple of properties recall from pre-calculus. E to the ln of x equals x, and ln of e to the x equals x. Those are the inverse properties between ln and e. So in this case, what I'm going to do is to use the first property. So this will be 7 to the negative pi times e to the ln of 7 to the x plus pi. Alright, if we cross cancel this e with ln, we should get the 7 to the x plus pi, which is this one right here. Alright, so well, but in this case the reason we do this is so we can do the following. In this case, we highlight this, and we're going to use the smackdown rule for natural logs. I'm going to write this in front of the ln, and this will be 7 to the negative pi e to the x plus pi ln of 7, and we now have an exponential function of a base e. That's going to be e to the u, where our u, again, what's our u? U equals to x plus 7 ln of 7. So 7 to the negative pi sigma n equals 0 to infinity of u to the n over n factorial, where our u will be this expression here. Okay, need more space. That's x plus 7 ln of 7 to the n over n factorial. And finally, let's write this in terms of, okay, number one, I would like to write this 7 to the negative pi in the denominator with positive exponent. So that's sigma n equals 0 to infinity, and that's ln of 7 to the n, and x plus 7 to the n over 7 to the pi times n factorial. Final answer. And well, of course, this is an exponential function. See, this is the power series of an exponential function, so the interval of convergence will be negative infinity to positive infinity, right? And I'm going to stop the video over here, and in the next video we're going to do the reverse process.